Hello, welcome to the incoming course, Fundamentals of Astrodynamics by Dr. Ayoshola Ogundele. Course description: the science of analyzing the motion of natural celestial bodies, such as planets, stars, moons, and artificial satellites, applies the principles of dynamics, particularly Newton's laws of motion and gravitation, to understand and predict the trajectories of spacecraft, planets, and other objects in orbit. Astrodynamics field is traced back to the early astronomical observations and development of mathematical models, which began with the ancient Greek astronomers. Kepler's laws of planetary motion, derived from Tycho Brahe's observations, gave humanity better understanding of orbital paths. The foundation of modern astrodynamics was laid by Newton's laws of motion and law of universal gravitation, which are useful for space research. The launch of Sputnik 1 in 1957 ushered in a new era and renewed interest in astrodynamics. Since the launch of Sputnik 1, there has been increased interest in using astrodynamics principle to study the dynamics of celestial objects and artificial bodies and to use it as an important space dynamics tool. Astrodynamics is fundamental to a wide range of space activities, including satellite operations, space exploration, and space situation awareness. Astrodynamics is crucial for various activities: space mission design, trajectory planning, and understanding of complex interactions within multi-body systems like our solar system. This course is divided into 7 modules: Module 1, Module 2, Module 3, Module 4, Module 5, Module 6, and Module 7. Module 1, Vector Analysis in Astrodynamics. Module 2, Celestial Objects. Module 3, Newtonian Mechanics. Module 4, Satellite Orbits. Module 5, the Keplerian Motion. Module 6, Orbital Position and Velocity as a Function of Time. And Module 7, Spacecraft Observation Systems. Module 1, Vector Analysis in Astrodynamics. In this module, astrodynamics vector analysis, involving using vectors to describe and analyze the motion of celestial and artificial objects in space, is presented. Astrodynamics vector analysis involves using vectors to describe and analyze the motion of objects in space. This includes position, velocity, and orbital elements, and how they can change over time under the influence of gravity. By using vector equations and transformations, engineers can calculate trajectories, predict orbital behavior, and design space missions. In addition, various applications of vector analysis in astrodynamics, such as orbit determination, trajectory design, orbit propagation, and maneuver design, are presented. Module 2, the celestial objects. This module presents brief discussion of celestial objects, naturally occurring physical entities in the universe, such as stars, planets, moons, asteroids, and galaxies. The celestial sphere, celestial longitude and latitude, precision, notation, and variation of latitude are also discussed in this module. Module 3, the Newtonian mechanics. Astrodynamics, as applied in space missions, heavily relies on Newtonian mechanics, specifically Newton's laws of motion and the law of universal gravitation. These principles are fundamental for understanding and predicting the motion of celestial bodies and spacecraft. Brief discussion of the Newtonian mechanics are described. Module 4, Satellite Orbits. Different types of satellite orbits, the paths that satellites follow as they travel around the celestial body, such as Earth, are also presented. Satellite paths are determined by gravity and the satellite's velocity, and they can be categorized into various types, each of them with unique characteristics and applications. Module 5. The Keplerian motion. This module presents Keplerian motion that describes the movement of objects in space, specifically how they orbit each other, as defined by Kepler's laws of planetary motion. These laws, developed by John Kepler, detail the elliptical paths of planets around the star, the speed at which they travel, and the relationship between their orbital period and distance from the star. Module 6. Orbital position and velocity as a function of time. This module presents orbital position and velocity as a function of time. In astrodynamics, orbital position and velocity as a function of time are crucial for describing the motion of objects in space. And Module 7, spacecraft observation systems, are presented. Spacecraft observation systems are a network of satellites and instruments designed to collect data about Earth's environment and phenomena from space. This module explains the contribution of astrodynamics to spacecraft observation systems. To determine the orbital position and velocity of a celestial body as a function of time. The learning objectives are as follows: understanding of how to calculate spacecraft trajectories, predict orbital behavior, and design space missions using astrodynamics vector analysis. Ability to be able to develop Newton's laws of motion and the law of universal gravitation and understand their practical applications. Identification of satellite orbits and their usefulness. Understanding of Keplerian motion. Ability to develop orbital position and velocity as a function of time. And understanding of contributions to the spacecraft contribution of astrodynamics to the spacecraft observation system. Thank you for your attention.